Okay, my name is Venkat Pulela. I know half of this room, and few others also seem to know me. Sonic is bigger than a community for me. It's a family. Both my children are working. One on pins in Google, another is doing some kind of internship of sorts between Linux Foundation and Google is trying to do, I think, Alpine. I ask them, what are you doing? They don't tell me anything because of confidentiality. Pardon? And also I was part of Cisco family, Broadcom family, so all of us are one big family, right? So it's good to be here. Before I get started, I want to introduce, King Shuk. You want to stand up and wave so they can ask you the tough questions during the lunch. It's first time for me to present somebody else's slides. Usually when I go to a P4 conference, I would have coded it myself, or I know the hardware, software, whole thing. But we'll manage, right? We have a clicker. Our next slide, please. Okay. Quick agenda. We'll talk about Dash, P4, behavioral model, and then I'll try to skip reading the slides, and I'll give you some insights. We'll do faster that way, and feel free to ask me questions, right? How many of you are aware of Dash? Okay, good number, right? So a lot more don't know. So your TOR, your leaf, spine, whatever your network is all Sonic. When the same Sonic, when you take it to a smart NIC or IPU, DPU, or an appliance where you took a server and put some of these cards and made it into an appliance, or you integrated some of these IPU, DPUs into a switch and make it a smart switch, suddenly Sonic project becomes Dash. So it's open source, uses Sonic, part of Linux Foundation. The whole idea is that how can we bring enterprise scale and performance back into clouds? Okay, but they have all. Clouds are highly performant, but where exactly is there is a gap, and can Dash focus on two things, right? One is how do we optimize, and how to do it for stateful workloads. So these are the two keywords for Dash in terms of using the hardware accelerators to kind of accelerate the services that are happening, right? And the form factors we already talked about. The IPUs, you can put it on a NIC card, put it in a server, and can we use it to do some acceleration? Can we, like I said, put it on a server and build an appliance and keep it in the network? So whatever traffic you want to accelerate flow-based features, you kind of, not tunnel, but make the traffic flow through it, and then can it do it? Or if it is fully integrated into your network, if it is in your TOR, it becomes a smart TOR, or you have a smart switch, right? So it can come out, the same technology can be used, consumed, developed in different form factors, right? So that's Dash project. And these are the typical services. So if you are running a cloud, you can very easily see why these things are important, right? So when you go to a cloud, you create, everything is virtual. You create virtual networks, and you want to connect them before you even do anything. So VNet to VNet is a service. How can you accelerate? When I say accelerate, these are not millions of packets per second. I'm old enough to see 180K PPS was like the coolest thing that happened, and we celebrated, right? And forget the flows. So these are tens of millions of flows, right? 25 million is the baseline, right? And how do we build that? So VNet to VNet, then the peering, you can see, right? How do you tunnel? How do you connect your branch offices or your multiple offices to back, for hybrid cloud? How do you connect through a private link? These are typical cloud services. So the same set of services need to be accelerated. So Dash, when it says the Dash provides you certain APIs, that's the APIs are for the same, right? Before I get into so-called, the hero tests and things like that, when the Dash project started, it's a community project. We could have written what is Dash in a very nice functional specification in English, right? But the decision was that can we use P4 as how many of you are aware of P4, right? Good number, right? So I would like to claim I built the first hardware-based P4 switch on Doppler ASIC at Cisco. I claim because you can't verify these kinds of stuff, and it offends always somebody, right? But as an industry, we always had programmable silicon. So we never exposed it to end users, in the sense if you are a Cisco user 10 years back, you couldn't have designed your own thing, or in agentic era, you type a command, you got your truly software-defined network, right? When your command can describe the network and implements in your hardware, that will be cool. It can be done. We haven't done that. But P4 is a language where you could describe your data plane, and then you press a button, try to automate as much as you can, and then it'll get compiled and programs your programmable hardware to give you the functionality you want, right? Whether it is your Silicon One or Trident 4 or now Trident 5 is programmable or not, I don't know. Broadcom guys can attest to that. So they can suddenly start doing features that you didn't think of, right? With AI and custom congestion control protocols and all these things coming up, these kind of technologies become very, very useful. When I demonstrated this 10 years ago, maybe it was ahead of time. Everyone looked at it and said, looks cool, keep it to yourself, right? Nobody bought nothing. But 10 years from today, from that day now, P4 is a good way to describe your functionality and get to use software-defined hardware. But the idea of using P4 also took another role in the industry, which is to, in an unambiguous way, in a verifiable way. Like there is formal verification is a big area, whether it is for hardware or protocols or whatnot. Some of you PhDs know this, right? So you could describe in a language and formally verify that there are no bugs in it. I would say issues. There could be contention, there could be race conditions and things like that unknowingly creep into your protocol definitions or state machines. Those can be verified. So that's a value of a formal language description. So that is the aspect of it we picked up. So we started describing what is Dash and these Dash services and the way packet and flows and flow handling and stateful flow and packet handling is described in P4. Okay? So that is the whole beginning of Dash project. I'm going to skip some of that. There's a bunch of advantages. The advantage of doing something like this, very formal and a systematic using languages and compilers, is that you can automate a lot. I mean, there are a couple of presentations earlier. Great work, by the way. We need more and more. There's a lot of boilerplate code that gets done. When we worry about agents coming and replacing software engineers, I think those are the jobs that will go away, my personal opinion. But it's good, right? Sometimes it's good if software puts us out of our misery in certain areas, right? Some of us should celebrate that the boilerplate goes away. But at the same time, because we used P4, a lot of artifacts could be generated, automated, right? And so that is very useful in terms of testing when it came to testing. That's on the functionality side of things, right? That's on getting the Dash appliance or Dash software or Dash behavioral model being built, right? P4 has a very nice testing ecosystem. All that could be reused, okay? It also means we need traffic generation part of it, right? Typically in a system, the device under test is simulating, emulating a part of it. Rest of it is emulated by traffic generators. In a loose way. So there is a containerized traffic generator called XIAC that Keysight has. So we integrated these two. So both these building blocks were needed so that you could really build a testing workflow where actually yesterday I spoke to the guy, Chris Sommers. I have some of you know him. Whether it is in terms of Psi or Sonic or Dash project, some of you might have worked with him. Right, I spoke to him. He said, hey, don't forget to mention that you can get 5 minutes to dopamine. That's what he said, if you know the dopamine, right? How quickly you can get to your first success. He said with 3 commands, you can run the whole thing. And it happens within 5 minutes. I think whenever somebody is getting started on Sonic or Dash, this kind of automation is extremely important. The very first thing you do is going to break. Sometimes people get discouraged and they go away. Right? And I myself have done a lot of software releases where when it didn't do well in the beginning, even though it's a really good feature, it didn't take off, right? So this is very important, but the building blocks for this was fully automated behavioral model generation using specifications, and then containerized ecosystem and system test beds, right? So this allowed us to get to a completely automated system very quickly. There are 4 pillars to, like, Sonic Dash kind of thing. And now we talked about the behavioral model, some level of automation. How do we do performance testing and scale? You can't use containers for that. You can, but there is a way you have to integrate containerized infrastructure. So the last pillar is where I'm going to focus on a little bit and get into the hero test. Before I go there, maybe I'll touch a little bit. These projects are cool. If I step back and look at it, why some of us are all getting together and are able to do is there's a lot more industry-wide code design happening, and that's what is allowing us to really get requirements from somewhere, and somebody else is doing some models, and then products, right? So it's good to see industry evolving this way. So Sonic and Dash both are good examples of this. And then so that's the background, and now we jump into the main topic, which is hero test. So if you have a Dash system, how do you test the performance part of it? And how we developed, and I want to share some insights, some challenges. Other slides you can read yourself, right? Hero test is the one that kind of, anyone knows what is the hero test? Can I answer? Okay. So essentially, if you built a smart switch, and then now you want to declare it is Dash compliant. So if it is compliant, then you are a hero. Alternately, you are not a zero, but there is a little fuzziness there. But at least you are able to say that, hey, I am able to meet the Dash requirements. And then Microsoft is helping us with describing the requirements from a provider point of view, and also setting up some level of performance expectations. These things are very useful, because problem definition is half the solution, right? So that really helped the whole ecosystem with that. Hero test is what validates that level of performance can be achieved, right? So if you meet, then you are a hero. So that's the reason for that hero test, is my understanding. If somebody knows, we can clarify. And there are a bunch of services. When you want to look at services are how users consume that performance of your appliance, which is accelerating those flows. But when you peel one level down, there'll be details like, how many flows per second, how many flows per ENI, how many prefixes are allowed in your ACL and things like that, right? And you want to know to what extent can you accelerate without dropping packets, or at what point do you start seeing issues with this level? Because 25 million PPS is another level of performance than of course, we got used to it in the last couple of years. But when the Dash test is getting started, right? And the idea is that, can you do the same level of tests under duress? You're able to do 25 million PPS or connections per second, but can you do that when there is an attack happening, right? Typically what happens is, if there is some DDoS, or even if there is a specific malware attack, some of them can affect your state machines in your switching pipelines, and that will have an impact on your on everything. So can you do the performance testing while doing the attacks, right? And can you do the connections per second tests while maintaining full capacity of PPS? So in a way, it's not just about conforming. In a way, you're trying to test the boundaries of multiple dimensions at the same time, right? Because let's say you do come up with a connections per second test, right? You send a lot of connections, and it says, okay, you can do 25 million. But 25 million connections may only consume, let's say, 30% of your packets per second, right? Because just to optimize on the flows, you're sending small flows, right? But the idea is that, can you do both the dimensions? Can you do 100% of your connections per second by putting background traffic, and under that condition, can you do connections per second? And while that is happening, can you throw some attacks into the picture, right? So the test itself, takes care of all those dimensions. These are all bunch of numbers, but it still boggles my mind that we are talking about such big numbers. Look at the number of ACL prefixes, right, for a 1.6 tera switch. Look at the TCP or UDP flows, right? CPS still wakes me up in the night because I've seen very small rate switches long back. So these scales are mind-boggling that ASICs can do. So how do you build these tests, and what are the challenges, and what are the learnings, right? I won't focus on the details. Couple of things. If you really want to test ACL scale, imagine you set up lots of access controllers. But the hardware, there are multiple ways it can get implemented in hardware. There are algorithmic TCAMs, and they tend to be a little fuzzy in the sense that earlier TCAMs were very simple. There is like a you will have 1 million entries, and then every entry has its own mask and value that whenever a packet is received, you apply on. And later, bunch of entries started sharing masks. So there are certain artifacts inside hardware that can make this whole thing non-consistent. Because when you do these tests, you should be repeatable and consistent, right? And there are other funny things, right? Even I remember at Cisco, we put in a small cache in a switch, and we shipped it, and somebody tested it, and their test was such that everything was hitting the cache. So suddenly the performance looked like 10 times better than what it would be. And the guy started writing a nice article about it. And we had to go tell him, don't write that because you only tested our cache, not the whole system. So how do you kind of understand various ASIC architectures out there and the issues that you may face in terms of route aggregations or ACL compressions and things like that, right? I'll give you another example, right? If you take an IP address, right, 32 bits, let's say we say it's, let's say the IP address is 0001, right? Right, when you look at in binary, it'll have all the 31 zeros and 1. To match this, right, a regular expression would have been 0, 0, I mean, not of A0, not of A1, all the way, and the last one would be A1 as A31, right? So there is a way you can match an IP address by putting some bunch of gates or some kind of a regular expression. Typically, what happens is when you take an inverse of that regular expression, that one IP address explodes into 32 minterms. Is it making sense? Some of you did the digital logic would understand. So that means describing something is easy. Describing an inverse of that is very complex. Okay? That means describing Venkat is easy. You say Venkat, Venkat. You say everything other than Venkat in the universe to describe will suddenly become many lines. You can obviously imagine why, because other than Venkat means all of you are showing up in this room. Describing all of you takes a lot more rules. And there are optimizations that are put in TCAMs to capture this negative thing. That means if A takes certain size in TCAM, A bar can take more size or less size, and people use that to optimize. I did some very early work on this, I don't know, 30 years ago, I guess, right? I'm revealing my age, but that's okay. Most of you know my age now. So how do you test so that such things are not impacting your consistency, right? And you can read the slides, people try to leave gaps so that things don't collapse, or aggregate and things like that. Does it make sense, right? So those things were done. Details you can read. I'm only giving you high-level view, right? And in terms of methodology, how do you want to test it? So in the beginning, you cannot directly go and do those massive tests that run at millions of PPS. There's a lot of instability. I spoke to the guy who did it for the first time. When it's all done, it looks simple. We said 3 commands, if it is working, must be simple. I said, yeah, it took 6 months to get there. So typically, we were using vendor-specific APIs to program the DPUs to a certain state. In the beginning, it's still a hack, but kind of do that, and then go to SI, and then go to full dash, right? It does take multiple iterations to get there, and you can obviously guess that, we were doing incremental testing in terms of, can you do just a one minimum viable configuration and a one flow test before you go to something called a baby hero test, and the real hero test is a 25 million flows test, basically, right? There are many dimensions like you saw in the table. I'm oversimplifying, right? So this is, again, common sense, crawl, walk, run. Even when new switch vendors, new hardware, as you are getting started, you will have to go through this. And what is in hero test? The idea is not, hero test is not a pass or a fail. It's not a hero or a zero test. It's not, right? Idea is to find a bound, a range, mainly because of multiple dimensions, right? CPS under packets per second limits, CPS under attack like that, right? When multiple dimensions come up, it will become fuzzy. No matter how much you make it consistent and reproducible and tested, would you guarantee the same performance in the field, in the cloud? It is difficult, right? So the whole idea was to kind of come up with a band within which the real performance falls, right? So you're looking at the best case curve, then you are looking at the worst case curve. And in both the cases, you really have to understand how things work at a lower level, at the ASIC level and ASIC architecture sometimes. So you cannot do black box testing. Even if you are doing black box testing, you need to have like a, an architect or somebody who worked on these TCAM architectures and ASIC design, multiple pipelines, buffer sharing. All that knowledge is required. Otherwise, you won't be able to get the worst case scenario, right? Testing is an art. We can automate once it is done, but you will never, get to this level of, right? So best case and worst case bands is the whole idea. And the reality, hopefully, will be in the middle. And I'll show you a graph just to get an intuition later, right? Packets per second, latency, throughput, I don't need to mention. Of course, somebody would have tested. We do that test, right? But let's focus a little bit on connections per second and give you a little bit of view, right? What Dash mandates is a 6-packet flow. That means you're not really doing any data transfer. You're just establishing a connection and you're tearing down a connection. We had to introduce another thing in the middle, mainly to get the control over the amount of traffic we can pump, right? By changing the packet size, which we want to control the amount of load we are putting on certain aspects of our certain hardware modules. So we made it into a 7-packet test, which is HTTP. HTTP, I don't know what HTTP, get or put or something, most likely. One of them, we don't know. But we put that in. And so that was something introduced. So we're not deviating from the 6-packet flow, but got good control over it. And other issues are like, how do you handle retransmits? When you have 25 million flows, can you maintain so much state in a traffic generator, right? A ASIC that's of the size of your thumb required a rack of hardware to kind of connect it and test. And we can't do that all the time. And so, finding ways where you are maintaining a sliding window of state and letting connections age to some extent, right, became very important. Otherwise, there is no way you can keep so many active connections. At the same time, you want certain number of active connections while doing, CPS tests. That sliding window of state and making sure that you have a decent enough state machine which can handle one order of packet drops and retransmits, right? And then again, performance differences in terms of if the connection initiator closes the connection versus the server closes the connection, there are performance differences, right? How do you surface those issues, right? So those are the things that we had to look at. And of course, right, just to make sure that you're operating at the full table size, you tweak your aging timer. There are 6 or 7 kinds of aging of flows across the industry. But here, at least, this is just usage timer is what we use, because when you make it so complicated, your consistency and reproducibility becomes very difficult, right? Couple of numbers on, typically 50 to 80% background traffic. and leave 20 to 30% for the CPS. And when you do that and you kind of change the packet size to kind of hit the boundaries, right? How do you hit the boundaries in 4 or 5 dimensions, right? So it does become like a little bit of an art. And like if we are doing a baby test, or if you are doing, at what point do you consider failures? Just because you got one packet lost, if you undo, or you say that, hey, I'm no more testing, that's not a good thing. Typically when you are anywhere from 1 to 1,000 packet, again, soft definition as a community, right? Up to that level of packet loss is considered okay, unless your packets per second or flows per second is very low. If a million or 2 you hit that, then you have an issue, you want to debug. But certain things you don't want to get into debug mode, you want to keep pushing that, right? So maybe this will give you a view that it's not a fail or a success test. Hero test is multidimensional, you're pushing the boundaries. The upper boundary is where vendors will show the best possible. Again, a lot of vendor-specific discussions that happen. The lower boundary is what, as a tester, you need to kind of look at and bring out. And then the other takeaway is that, how far can you go with 0 packet loss? While it may look like is okay, common, and it can be done easily, there's so many vendor-specific optimizations that can hit, and you want to do it in a vendor-neutral way. Because like I said, right, if you use the cache alone, you could look like that. 128 entry cache could look like you suddenly have a terabit switch, even though you don't have, right? Small caches are miracle architectures, right? So how to push that number in a vendor-neutral way and making sure that really has a meaningful value is the big thing. The hardware looks like this. Yeah, some of us who are I think our industry people get excited seeing wires and boxes. So I thought I'll just put that in there. We're not weird people, don't think that. We get excited, right? This is cool stuff. I'm going to skip some of that. Call to action, like I said, for me at least, it is becoming more from a community to a family. I'm going to ask you for more T-shirts for the family. I'll show you later. I have an extra small and an extra large kid back home, so I'm going to take on that. But I'm the medium if you're thinking what happens, right? We are contributing to both Sonic and Dash. Work together. If you have anything new that comes up, if you want to do it as an industry-wide co-design, open traffic generator and things like that. We ourselves have come up with an open interface to traffic generators that we put our product behind. You could have your own free T-Rex, and I forgot what the old Cisco something else was called inside. Right? Open free is part of the multi-vendor. We fully embrace that, and we should, right? There are certain things that require hardware that people have to pay, but others, I think, we have to build that. We are open to that. Any new projects, community, open to collaborating. Thank you.
Questions? Yeah. Let me pass the mic.
I was about to bet that there won't be a question. But, yeah.
Yes.
So there was one statement about the setting the age timer to high value and then benchmarking that, right? If we are doing that, then we are not really aging some of the resources and then trying to evaluate the benchmark, right? So how are we going to evaluate the right performance values with that statement?
Very good question, right? Because you're really trying to find the lower boundary. Lower boundary, we have to imagine 4 or 5 dimensions, right? Lower boundary will be hit. We don't know in what conditions it get hit, right? So, but there is an implication in terms of when the whole table is full. Under that condition, you want to see how well the new connections per second happens. Because you could have a hashing function, your hash and hash probabilities. Is it a TCAM-based hash, right? Right? I mean, TCAM-based hash essentially is a 0-1 complexity. I have designed a collisionless hash, 10, 15 years ago, again using TCAMs. So there are hardware implications for such things. So that statement is to just push the boundary under one condition, one dimension,
okay.
right? The way, right? Imagine that very first flow-based which I implemented 96, I think 97, 128K flows is the hardware. Only 32K flows were advertised because of the probability, right? 99.8% probability of hitting was only at a 32K. You're advertising 1/4. So then we put in a TCAM, which is instead of a 17-bit hash, you could do a 34-bit hash, which suddenly became like a huge, I wouldn't say infinite, huge virtual flow table. And that kind of reduces, first you hash into one table, and each bucket is like another hash table. So that's how you can reduce hash collisions, right? So these kind of techniques, how do you find their limits,
Okay.
right? So that's where I was saying, right, you need to know a little bit of hardware architecture and then do that. So I don't know, does that explain?
Yeah, this is one use case that you are trying to tell.
In way because 5 dimensions will look weird, right?
Right.
And then you want to go push this limit and then come back, push this limit, and things like that, right? Same thing, while doing that, start doing an attack on the background and see what happens. That
Right.
means CPU is loaded, let's say, for whatever reason. That means your fast path to faster path to slow path, right, which slowest path, the process switching, certain packets are going there, and because of that, you could not update something in the hardware. What if you have hardware-based IPC? That means you found some state in the CPU,
Right.
and the delay it takes to push it and programming into the hardware that can vary. So that could cause your connection establishment rate, right? So how do you push these things? So you need to be a little aware black box testing won't work.
Right.
To push each dimension, you will have to come up with these kind of statements and
Right.
walk that space in different directions.
Okay.
Make sense?
Yeah, thank you.
Thank you for the question. Otherwise, I will have to walk with
Yeah.
questions. Buy one, get one free. So you got the free. I'll pay him later.
Yeah, not specific to this hero testing, but there was one slide where you mentioned about this open programmable interface, right? So from Sonic Dash API and open programmable, are they coexisting, or how is this being used in the current systems?
I'll repeat to tell me if I got your question right. OPI is a open programmable infrastructure Linux Foundation project. Was there any reference to that?
Yeah, and even there they talk about APIs. When we go about Marvel, I've seen those demos.
So I chair the board of OPI Project Linux Foundation. It's again DPUs and IPUs,
Right.
Same community there. I think, and then we are part of both, right? Here, I think Microsoft is cheerleading the whole industry towards something very specific and a set of use cases. OPI is a lot broader. Community, maybe tier 2, tier 3 service providers, and then lot other use cases, right? So the use cases are slightly different there, right?
Okay.
But we are trying to see how we can collaborate. Maybe Dash security, can OPI help and things like that, right? And so the OPI makes it a little broader. I think Dash is moving really fast with a set of goals, right? This is more like OPI on steroids, let me put it that way.
Okay,
I
so
don't know, did I answer you? Yeah.
so when we say the Psi Dash APIs, right? So is it like similar to OPI interfaces? We have also implemented Psi Dash APIs for use cases like load balancers or other things.
Good question. So Sonic ecosystem, we always use Psi and layered architecture. Psi APIs will get enhanced, then Sonic uses it, right? So that's why when we get these new IPU, DPUs, Psi has to extend to get to those APIs. As of now, there's not too much of an overlap, but maybe OPI and Dash needs to collaborate so that, and then start solving different problems. That becomes a different use case, performance. The hero test may not apply to OPI because the tier 2, tier 3 service providers, their proof points, the kind of hardware they may use, and where they optimize their software and hardware co-design may be slightly different than Microsoft scale or Google scale, right? So that's where, while certain APIs are okay, some of these tests may not map directly. But idea is that it's important for them to collaborate if that's where we are getting it.
Okay.
since your journey has been very long, so just I want your...
Are you calling me old?
No, no.
It's okay, I'm old. Yeah,
That horizon is vast. So your thought on, you told about that flows. So I have encountered those things in past in Juniper when we were doing for the like service provider things. When what you said from the 1 dimension, 2 dimension. So if we see the flows thing from your thoughts on the flows on the rack solutions actually. So because if you see the traffic and data, now it is in petabytes. So what it used to be in 10 years back, traffic in 24 hours, it is now in 1 second actually, according to that VNI of Cisco. So your thoughts on that actually?
Yeah, so good question for me because the very first layer 3s we switch, we built at Cisco long back. I'm using company names because I worked in multiple vendors. It's an open community behind, and even though we are recording, we can share. Those details are old, right? So I don't think Cisco will mind. As a family, we spent 100 years at Cisco, so I can use Cisco and they won't mind, hopefully, right? Build the first layer 3 switch was a flow shortcut switch, right? Packets go to router, come back. And things have evolved. The flow state you want to maintain in the switch started growing, but only 20% of the customers need that flow state. So suddenly the 80% are paying the price for it. That's one view, right? The other view is that imagine you put 25 million flows in a switch, okay? And one packet comes in and only 1 out of the 25 million flows gets lit. What is happening to the rest of the hardware? It's like you bought a fancy car and you're making it sit and you're not using it, rest of the memory. Some of the hardware designers can relate to this because they think slightly different than software. I did both Verilog and C++ and ones and zeros. I go both sides depending on the situation. So that was the inefficiency. So that's how these flows and flow state has moved out and suddenly became middle boxes. The very first switches had firewalls, load balancers built into the switches. And they moved out because we don't want everyone to pay the cost, only few guys to pay the cost. And they are coming back, right, in these form factors now. In a way, DPUs, when I see, those middle boxes are coming back. Are they coming back and are they fully getting integrated? Smart TOR or smart switch is where they are getting integrated, right? So I see it as a good thing, but also the system architecture, right, that one box architecture is becoming a rack scale design. I don't want to go to AI, but that's the reason. So I think what we used to call a box is not box anymore. So and you will see more and more of it, right? Your definition of a system is going to go from a pizza box to maybe racks. So that's a good sign. But there is still one problem that is not solved in the industry. If you allow me to. I can give you very detailed explanation later. It takes 10 hours. But this one insight I want to give you, having done flow switching for 35 years, right, is that the gap that we have as an industry, which Dash has solved in a certain way, if you look at how there is a stateless flow and a stateful flow, and if there is a miss, we come back and add, that is where the gap is. In the network, you get some information, something, you got some insight, okay? And it comes to the controller. Controller knows. So there is a delay in getting that state or information back to the controller. That's one delay. Once the controller knows this information, how quickly can you put it into the hardware and make the network reflect that change? That is another delay. That's even bigger delay. Imagine, right, in the olden days, a packet comes in, it sits in a queue in a CPU. It's not even a controller, it's a route processor. You need to get context switched. And then somebody receives, looks at the packet. Now we understood, wow, there is some link dropped, I need to do something. And by the time this guy creates another message, IPC back, some other processor receives it, then your SDK, by the time you program, the flow is gone long back, right? So that path optimization is where there is some more innovation needs to happen. And incidentally, a lot of these are already done in the past. One of the things I see with everything going on now, everything I have done twice or thrice. That means the same history repeats, right? In the past, there are hardware implementations. I won't mention the company names. They could send a packet in line that goes, it's an IPC to hardware. That means your software process or a container or a VM could send a packet and the packet is consumed by your ASIC. So the other side is not not a VM to VM, container to container. It's not a process to process. Process to ASIC inter-process communication. Maybe it's not IPC anymore, IPCH or something like that, right? Software to hardware interface. That work was done because that's the fastest way. Packet comes in and you are switching, ASIC will switch and create a entry and then the packet gets dropped, right? But that also opened up security holes because when packets can come in and create entries and act upon your data plane, it can cause issues, right? So they were, how do I say? We went back in those architectures, right? But that has to come back because that's the only way SDN, true SDN, can scale because the controllers at that scale have to disseminate the information and affect the information, right? There's a lot more challenges, but I have to talk to you separately because you have like 196 pipeline stages. If the first stage maintains some state, how do, or you write something, how will the second packet use? And like, hardware, software is a very complicated field, right? I don't want to spend too much time. Does that answer? Is that what you're asking? Okay, yeah. Okay, yeah, talk to me offline. I can give you a lot of stuff. Yeah, thank you.
Hey.
Are we okay
Venkat.
on time? Okay, yeah.
Hey, Venkat. He's our NPL and P4 guru, so I can ask anything. So anyway, first question is related to stage. I think you already answered. Is it possible to simulate a stage, pipeline stage and slices in this Dash framework? Example, a TCAM. We want to look up parallel lookup. That is first question. Second question is related to COS. Is it compliant for COS OC COS SAI test as well as snappy test, which is put up in our OC community? And for example, we can test anything for lossless. We can go for PGMin and shared DB and to the level of headroom. Maybe with one ITM or two ITMs. Might take TD4 because an example. Can we simulate that kind of testing here? And third part is related to PFC deadlock. Is it possible? Because
the second question I can't answer. I need to get somebody else.
Okay.
The PFC deadlock, I think there is a solution. People are doing it.
Okay.
But first one is interesting. I'm still a techie deep down.
Okay. The second one is the OC. We have a large test suite related to COS SAI and snappy.
So
okay.
I'll connect you to the right. Let's talk about the first one though. Can we
Thank
simulate, emulate all this stuff at that level of detail? No. But I want to, again, as an industry, I just want to give you some insight that I get by being in my role, right? I think all the hyperscalers, where they are heading, where I see the whole industry is heading, I'll make few statements, bear with me, is something called design to deployment continuum. At least that's the vision I go pitch and different people have pitched it, so I don't want to take, exclusive claim for it. Certain terms are mine and I know them, right? So what that means is that when you don't even have an ASIC, you have Verilog, can you test? And when you do from pre-silicon to post-silicon, all the tests typically are thrown away and then some other tests are done. There is one nice slide from one of the companies, I don't want to mention, where they do 19 tests before things come out in the whole so-called continuum. And then, and each one is a separate team, separate test framework, separate everything. So when I say continuum, we want, again, I'm going to make a statement. You can challenge me on why I should do it that way. That we'll take it offline. I am claiming that we need a system test bed at every stage. Same system test bed that you have in real deployment in your system test. Whatever is in your system test, in your integration test. Integration, same as unit test. Post-silicon, pre-silicon. I'm saying you bring your system test bed to pre-silicon. That's the only way you can solve AI class of problems that we are seeing right now. I know I don't want to digress, AI is another, but that's what is happening, right? And that improves your time to market. Your pre-silicon to post-silicon, the bring up comes much faster when you have this, right? That means you need to have common APIs to traffic generators. That's where we did open traffic generator. Consistency, same thing. Product, you can go to whichever company, but same thing, standardized SAI, Sonic, Dash APIs. Whether it is pre-silicon, you should run your Dash on pre-silicon, right? And once the whole thing is same, then it's easy to catch test escape. Something You found a bug in your system test bed. Typically in a company, you file a bug, it goes to a developer. The guy is busy. What will they do? They'll say reproduce and do something called bug ping pong, tuck. Ball comes to this guy, he continues to work, right? So it wastes a lot of time. So whereas if you have a full so-called testing continuum, then you can figure out where that thing escaped, where exactly we should have found but we did not find. For that you need this, right? So while we don't have this, I am seeing hyperscalers, I'm again saying generally, I don't want to mention, a couple of guys are a little ahead than a couple of other guys, which is fine, is that they are going towards this whole system test bed. Then the question is, why should I need system test bed in pre-silicon? A NVIDIA rack today has 600,000 components. In the past, each of us used to build one component and test it and throw it over the wall. Somebody assembles them into bigger components, throw it over, eventually becomes a rack, right? And also typically what happens is, somebody gives you a requirement, hey, make this work at 100 degrees centigrade. As a manager, I would add 115 and give it to my guys, and they will add another 15, and by the time you're designing for 200. So the margins used to be high. When so many components, we are doing tighter and tighter integrations. If you have seen that Meta paper on AI failures when they did Llama 3.1, Adi Gangidi and his team, great guy, admire him, he's my hero. Hope he's listening, or I'll show him this. Right, and they articulated all the failures. The failures are happening because you're integrating more components tighter and tighter. So you need to test your components in the context of system, and then only the scale, 1 million GPU scale problems will show up. So that is required. So the right context, right triggers and events need to be created even for pre-silicon. That's the reason to have the same thing. That is the vision. That's where most of the companies are going. Is Dash there? Not there yet at that level. We don't think we do pre-silicon, post-silicon kind of thing on Dash and Sonic yet, right? I mean, in a way, Sai is a separate project, Sonic and Dash are separate project. Maybe that's something we should look at, right? I think the moment Leva and Dave, I'll go back and meet with them soon, and then maybe that's the thing when they are moving to the AI. That could be the discussion, saying, hey, when we go to AI, should we look at the full continuum, design to deployment, right? Long answer. Okay, thank you. Go ahead. Yeah, so good question. Can I keep going?
Sure.
You stop me whenever I stop you.
I will stop you in 2 minutes.
2 minutes you stop, because I'll go for a long time.
Because we have 10 minutes.
So his question is that for that you need to have some simulation, emulation of that before the thing comes up. And they are available. So another way to look at it is, you're always doing system testing everywhere, no matter where. That's the claim. A system is made out of simulation plus emulation and real components. You want to imagine your system test bed to be that way. When you are on a pre-silicon, the whole thing is simulation. And later you will add some emulation. To me, again, simulation, emulation, everyone has their own definitions. Emulation is a higher fidelity simulation. Simulation to me is acts like a duck, quacks like a duck. That means API functionality, it's a duck. Inside, I don't know. If there is indigestion, I can't go in and fix it. Whereas if it is emulation, internal bugs I can fix. Real components are real. So in your system test bed in this whole continuum, the boundary between simulation, emulation and real keeps changing. In the real test bed, the whole thing is real. In the simulation, whole thing is this, right? Are there tools? Yes. Are there people who are building it? Yes. Huge, massive FPGA arrays are there. But I think where we are doing, I am doing some level of innovation. Keysight, actually, King Shuk, you should talk to him. He does a lot of research and does, has good insights on these things. Is how to mix simulation, emulation, and real. It's a speed mismatch. One can do few hundred million PPS. Simulation can do 5 PPS. I have also seen a 5 PPS, right, from that company. I don't want to mention the company. And how do you? So the innovation is in how do you connect the speed mismatch and call it impedance mismatch, being an electronics engineer, right? But right, how simulation connects to emulation, connects to real component, form a system test bed, and the percentages change as you go from left to right. There is a lot of innovation there to enable this kind of vision.
That's my point. We have to do a lot of iterations there.
It is happening. Hyperscalers, I will mention, I don't know how many billion, 70, 80 billion is what Microsoft invested this year in AI. all that is driving innovation. Sometimes, Keysight, or all of you, I'm sure, right, are partnering with these hyperscalers and playing in that ecosystem, and they're enabling these technology waves they're enabling, how do I say, this boundary to be moved, right? When Microsoft spends 80 billion, where is it going? Some of it is software salaries. Like, I don't know, he's saying not me, right? Not 80 billion? Okay. So, but